picture came, it was interesting that in 1916 already, 1915 is when Einstein produced his general theory of relativity. In 16 he already commented that just as in order to get the stability of atom, we needed to modify the notion of what was electromagnetic interaction. There will also be atoms, electrons will also radiate gravitationally, and therefore they will also have to be, the stability of atom has to be guarded against that. So therefore we will need the modification of gravitational theory also. So an idea in sense of you want some notion modification going away from classical theory to quantum theory was already anticipated or rather mentioned by Einstein himself in 1 year after GR. Now it's a little bit strange because his quadruple formula, which shows that gravitational radiation can be computed, was 2 years later. So what was this? So this was based on the idea that just as electromagnetism has radiation, so gravitation will similarly have it, because the idea based on quantum field, and if that is the case, this issue should also arise, and therefore one should think about it. Now if one estimates very quickly, you can say that typically for atom one will say that if a electron radiates electromagnetically, it should collapse into the nucleus in about 10 power minus 11 seconds or something like that. So multiply by the weakness of gravity, so you will net about 10 power 40 more time than that. That will still be way beyond what we understand of age of universe currently. But of course one should realize in those days universe was supposed to be eternal. There was no expanding universe, that notion did not exist. If that was the case, then of course universe has been there, so there is plenty of time left for the atoms to be unstable under gravitational radiation. So that was not as, now it will look like, oh come on, the numbers are so small, why do you bother? No, at that time it was not the case. This was mentioned actually in a blog post on Scientific American by Gorelick 2011. This is an article about the first effort at quantum gravity by Russian named Bronstein. It was again based on the idea that the earlier time when people talked about quantum gravity or quantum field theory, the one issue that they were concerned with was how do you measure the field? Is it in contradiction with the uncertainty principle that you will get from its sources or not? And that was one of the issue which occupied them. So in the same spirit, there was a paper written by I think Pauli and Bohr perhaps, I forget who it was. I didn't write it down. They proposed this theory and say, oh no, you can quantize the gravitational field the same way, electromagnetically you do it this way, it should not expect, they don't expect any further difficulty. However, it was pointed out that no, you cannot make the measurements of gravitational field as simply, and therefore there is some issue to be done. And this was identified by Bronstein as saying that to measure all other interactions, make measurements of fields by observing the probes, you can make the apparatus arbitrarily large, and so that to reduce the error. But you can't do that with gravity, because the more moment you make apparatus large, gravitational force is also going to increase. Therefore, there is no way to do that. Therefore, something else has to be done. Maybe one has to go beyond the notion of geometry. So this was already anticipated. I think Bronstein paper is around 1936. Of course, it remained in that, and regular quantum theory took over, and one went one further with that. Now next we come to, so that was electromagnetism and lessons we got from it. Strong and weak interactions, we have had wonderful lectures, very detailed lectures on this in these sessions. So strong interactions, of course, atomic nucleus being positively charged, you need to hold something together. So interactions, to how do you overcome that Coulomb repulsion. So strong force was postulated, and in the eventual elaboration with, we already had many talks discussing in great detail. It led to the colored quark interacting with colored gluons, quanta of non-abelian Yang-Mills fields. A weak interaction, analogous story, discovery of radioactivity and beta decay, and Murthy just now gave a very detailed discussion of this. The continuous spectrum of energy led to the identification of a qualitatively new interaction. Its elaboration again eventually led to the electroweak sector of the standard model with elementary leptons, their neutrinos interacting with W plus minus Z gauge bosons and Higgs boson. So this was already something which is elaborated in detail, so I am not going to talk about it, of course. All of this was quantum all through and through. There was no classical manifestation of this to say that, okay, here is a classical theory, you need to do something to make it quantum. The phenomenon was discovered within the quantum context, all the calculations were done in quantum context, so it was essentially a quantum show, if you like, and it's of course true, validated. So it was quantum all through and through, there was no classical manifestation. Gravity is exact opposite. It is manifested commonly through apples and stars and galaxies and whatnot, but nothing at quantum scale, none. So there is no immediate experimental compulsion of any sort. Any of the experiments that people, were used to spur the revolution in quantum mechanics of quantum mechanics. So there was no such experiment available. Even now, it is not there. So then one can raise the question: well, why quantum gravity at all? There is no experimental push to say that you should quantize gravity for some reason. So why at all you should worry about it? A valid question. People who do quantum gravity, of course, don't bother about this question because they are already convinced. But I think it's once in a while to ask the question, not so much to have the answer as such, but to be aware of what are the various things that are still unanswered and why you might want to consider quantum theory. Not just explaining a given experiment in a given context. That's a different story. So one answer, of course, is why not. All other interactions in the elementary form are quantum mechanical. They even hint at unification. So why should gravitational interaction be left out? May it lead to an inconsistency? This inconsistency issue is not something which is, at least to my mind, is not something as clear. At least I have not come across an argument which will tell me, okay, this argument seals it completely. There are various caveats which will be there, and so I'm just leaving it as this is a common argument people give. You take T mu expectation value and you will get, you can't quantize matter part alone, and gravity should also be quantized. That kind of argument, to my mind, is not sufficiently convincing. So, but let us note it because that is one of the arguments which goes around. The real argument, to my mind, the strongest argument is coming from the singularity theorems. So gravity is not just a force. That is something that all other interactions that we think of, electromagnetic, strong, weak, etc., intuitively the idea is that of a force, something exchange and something comes. Gravity, of course, does that, but it's not only the force. Newtonian gravity was, of course, essentially only the force. Gravity also has the manifestation of space-time geometry, and that was the clean, very distinct idea that Einstein gave. And it is the geometry is again not in the sense of doing something exotic mathematics or so. It actually defines our elementary tools of measurements, namely rods and clocks. All the devices, measurements of tracks, measurement of timing, everything that you do is related directly to space-time geometry. And that was the main message which came. So all of the experiments that we'll do will eventually have to be translated back in terms of this or vice versa. That being the case, we cannot completely ignore it. This was not the case with Newtonian gravity, which was a force, but in general relativity, that is something which is a new feature which has come. Secondly, so given this background of space-time geometry, which defines the relativistic causality, namely nothing goes faster than speed of light, so it will tell you that classically at least things which are space-like separated cannot influence each other. We incorporate that also in quantum mechanics and quantum field theory by saying that space-like separated operators should commute the microcausality statement and so on. Now, if you want the rest of the physics to be well defined and should have the notion that yes, here is the cause, there is the effect, even if you do it statistically, even if you do it with approximations and so on, there is some causal chain has to be established. Now, one can ask the question, what are the possible space-time geometries in which this is guaranteed? It is not always the case. The case that we normally do it is sufficient. Our Minkowski space-time is good enough for all relativistic calculations. All of phenomenology that you do currently is Minkowski space-time is sufficient. So one doesn't need to ask this question. But suppose you do ask the question, now that you have got Einstein has given this general theory of relativity, which allows various kinds of geometries, almost essentially arbitrary geometries, depending on the distribution of matter. Now, if so, then what guarantees that the stage in which you do all your experiments and observations will support the idea that you can have a cause and you can have an effect. Not only that, there is a well-defined notion of what is determined by what and is the determination complete. All classical. I am not going to quantum theory yet. Entirely classical. That requires this notion of well-behaved space-time. Now, there is a singularity theorems will tell you that if you want to have space-time with good causality, then first of all it should not admit closed time-like curves. It should not admit curves which are time-like curves, for example, or observer's trajectories. They should not come arbitrarily close to each other so that you will get confused whether this is the cause of the thing or effect. So that should also be avoided. Secondly, you may not know the metric well enough to define what is your light cone, and therefore you don't know whether something which was time-like or light-like and whether it's close or not. So given all these things, you can remove all these pathologies provided you use the condition of something called space-time should be globally hyperbolic. It's a technical condition, there is no reason to go into that. It's sufficient to say that not all possible solutions of Einstein's equations are admissible on physical grounds, so that they provide a stage on which you can do rest of the physics in a causally consistent way, whether quantum or classical. So, it's necessary that you restrict yourself to this class of thing at the classical level. Now, the thing is that the singularity theorem's content is of the type that, okay, this is fine, very well, you can, so what, we can have globally hyperbolic spacetimes. Now, the problem comes that there are still situations, especially two types of situations which were identified. We also know that matter can collapse under its own weight. In the stars we have already seen, neutron stars, etc. You can even go further and form black holes. Now, if they are collapsing on themselves, at some stage it is possible, I mean that is a mathematical consequence of the equations, you can form something called trap surfaces, where from if you try to look at emit light, light will neither go outward nor go inward, it will always be inward. So, that is called a trap surface. So, such surfaces can exist. Then the theorem says, suppose that the collapse has gotten to that far. Not every collapse will do that. Some collapse will simply collapse and form a star or an asteroid or whatever. Not everything will do that. But there exist situations where this can happen, and if this happens, then there has to be singularity. And singularity here means that trajectory of some observer or something will get terminate, it suddenly will not be able to extend the space time beyond that. So, some causal pathology will exist if that happens. Okay, fine. So, maybe you never get collapse, so that it has this trap surface formation. Second condition where this can happen is if your universe is expanding and is expanding with non-zero rate everywhere, however small it is, then again it shows that it must have come from a beginning which is necessarily singular. Again, singularity means that your model of space time will break down. Now, so here is a theory which says, identifies the possible situations where things can go wrong, and says that things will go wrong if these specific conditions are met. And then if that is the case, you cannot use your the model of space time cannot be used for making rest of the physics predictions properly, but some pathology will develop. So, that is the consequence that comes from analyzing of the theory itself. So, classical GR therefore is inadequate. So, the theory itself says that, look, under these conditions which can arise, I will fail. Now, if that is the case, of course, there is a situation, fine, these are all extreme cases, so one may say, oh, it is not going to happen in our lifetime, etc., etc. So, why bother? One can always take that attitude, but then I will take the attitude, if I have to only eat pakoras, I do not even need to do all the other things. So, if one doesn't accept those kinds of arguments, then yes, you have to do something to extend the theories, so that at least these situations are overcome in some fashion, they are managed in some fashion. So, that is the reason for, to my mind at least, this is the strongest reason one should consider going beyond classical general relativity, and anything we extend, the first thing we know after quantum theory, quantize it. How we quantize is a different story, that we will come to. Another situation which again motivates why quantum theory, again part of it has been discussed in detail by Sandeep. So, black hole thermodynamics, I will very quickly just mention the points. It allows the black holes, namely I just mentioned, collapse can happen and they form black holes, where these are primarily geometric objects, because all you can see from outside are is mass, angular momentum and charge, at least the macroscopic things that can be realized in astrophysical context. So, let us say even forget about the charge, because if the charge is positive, some other free charges will come and neutralize it, that is the idea which one uses. So, rotating objects can be there, so you can have black holes which are rotating and have some mass. So, no matter how the black hole is formed, it will still manifest only these couple of properties. So, that is all you can know about it. Fine, so be it. Now, consider processes involving such objects. Then you find, and this was discovered during the 70s, that these objects behave as though, so they will distort each other, so they will change their attributes such as their size, namely the area. They can change their mass a little bit, because you can throw something at it, it will absorb the mass, it can change its rotational angular velocity, it can change angular momentum, but all the changes are such, and this can be established as a mathematical theorem, that they take the form of, the changes in these values take the form of first law of thermodynamics, with a term which involves surface gravity multiplied by change in area plus other terms. So, this exactly has the form of this, and this particular term, surface gravity times change of area, it looks like TdS, which is the form of entropy and temperature. So there was no reason why in the mathematical theory perfectly well defined, why should such a relation hold? Is it an accident, just a coincidence or what? Well, of course, Bekenstein pushed the idea further and invented very many different situations to say, no, this should be physical effects actually. The problem was that, okay, if you accept it, then it has a temperature, and temperature means every hot body radiates, but of course nothing can come out of black hole. So what does that mean? So there must be something wrong. So Hawking actually tried to establish that no, this must be a coincidental thing. That's really a real feature, and ended up discovering that no, if you incorporate possibility of quantum mechanical excitations in the vicinity of these black holes, then yes, it can actually acquire temperature. Not only that, it will acquire temperature exactly proportional to the surface gravity. Now that was a non-trivial coincidence. Calculation was the first calculation, essentially semi-classical in nature, but it established that yes, there is little more than mathematical formalism analogy. There is something physical going on, but to do that, you have to allow for quantum mechanical processes to take place in the vicinity. So that was the new feature which came. All right, but this presents a new problem. I'm just assuming these things are given, new features have come, and that is to say that if it temperature radiates, fine, let it radiate, it decreases its mass, and temperature goes inversely with the mass. So more it radiates, more mass it loses, eventually it will disappear. Okay, so if a complete black hole evaporation takes place, then there is a problem. And the problem is that the first time the first set of calculations, semi-classical calculations which were done, which says that imagine a situation wherein you started with a coherent state, let's say classical, which collapses after forming a black hole. Hawking evaporation takes place, it disappears, and finally it has disappeared completely. I mean, that's the scenario that one imagines that happens, at least qualitatively. So we have gotten a process, a mechanism, so that a pure quantum state can evolve into a mixed quantum state. Now this directly contradicts the notion of what basic quantum framework should be. So that is one of the, one may call an information challenge, in the sense, are these processes really allowed or they are not allowed? So that's a puzzle. So depending on, I mean, most people believe that quantum mechanics is, its unitary evolution is correct. If so, then something has to be done to understand what goes here. Now to do that, one will have to understand what happens to the, whether you need gravity's quantum nature to be present to talk about the end point of this evaporation. Because as it's evaporating is still big enough, it's not too surprising that information quote unquote is lost, because part of it is inside and you don't have access to that, but fine, eventually it comes out. The question is what exactly happens at the end point depends on, because that time it's supposed to be, the black hole is supposed to disappear, which means it shrinks to size 0. Size 0 means size Planck length. If so, one would expect quantum gravity effects to be present. So if you want to resolve it, some notion of quantum gravity must come in. So this is one more reason or motivation to consider why one should consider quantization of gravity. Okay, so this is motivation part. So okay, if that is the case, let's begin and say, all right, we quantize it. In fact, people did immediately. And we quantize it the same way that you do for electromagnetism. That's the only thing that we knew. These are the two long range forces. So you consider propagators, perturbation theory and so on, and you get immediately into first problem, which was also mentioned by Sandeep, namely these perturbative calculations are not renormalizable. So you will always encountering more and more ultraviolet divergences, which are mathematical artifacts of the calculation, and they have to be absorbed by saying that, well, the parameters you are using in the calculation are coming from the Lagrangian and not the physical parameters, but they are mathematical entities you choose, and you are free to adjust them so that the finite quantities you construct out of it are the ones which are to be determined by experiments. Fine, this works fine for all the standard model interactions, QED, QCD, standard models, etc., because there are only finitely many such terms we need to be adjusting, and that is fine, we will live with that. We don't have to have all numbers to be obtained, but finitely many we can manage. So in terms of those, we can find out all the other predictions, there is a predictive power. However, gravity will say, perturbative gravity will say that that is not possible. You actually need infinitely many terms to be adjusted in this fashion, and therefore, okay, you can keep adjusting, but there is no prediction, because every new experiment you are going to need that. Then what are you predicting? You are just fitting the curve for different values. So this fails for the simplest approach that you will take for gravitational interaction. This itself is not a disaster, because it is possible to interpret these theories as effective theories. Namely, you say that even if there are terms which are conventionally by power counting are not renormalizable, you can say that I am writing this effective Lagrangian and say that I will include only those terms up to a given scale, which are relevant only up to a given scale of observation. And beyond that, if anything happens, I will say, okay, this particular calculation scheme I have chosen is not adequate, I need to go beyond and I will include more terms. This part can be done actually quite systematically. Again, you are reduced to finitely many terms, you can adjust it and you can make predictions again. So, effective field theory approach proposed by Weinberg, for example, in the early 80s or late 70s, it is possible to manage this non-renormalizable nature of gravity. So, it need not be a disaster and one does not have to close shop and go away. In fact, these ideas were used by Donoghue and his collaborators in 1995 to 2005. They managed to extract quantum corrections to the gravitational potential, because suppose you got this theory to work, what do you compute? In fact, I wanted to ask this question to Sandeep. Now that you have gotten your amplitudes under control, they are renormalizable. Tell me what is the corrections that you can compute. I did not get a chance to ask him that. Anyway, the analogous calculations have been done by in this Donoghue and collaborators, and they managed to extract quantum corrections, noticing that although the renormalizability issues affect the power law corrections, but there are non-analytic corrections which will come, they are independent of what these divergences are. So, those can be computed reliably, and they did so, and in that process they calculated the corrections to the both Schwarzschild potential, I mean far away from the body, you find out the 1 over r potential you get plus corrections, and the corrections then turned out to be go as LP square over L square. L is the length scale, for example, if you are away from the star sufficiently far away, so that the perturbation theory is done with Minkowski background. So, your background matrix should be sufficiently close to Minkowski, so go far away from the body, and then the corrections will be LP square L square, but these are utterly negligible. Yes, you can compute them, but they are so, I mean 10 power minus 66 divided by whatever, so this number is not even worth writing the decimal places. And this chosen cutoff cannot be removed. This is another problem, because the moment I start increasing the cutoff, I have to put more and more terms, and because of the fact that perturbative theory was not renormalizable. So, this cutoff cannot be removed. That means, we keep playing the game, all that you get doing a lot of work and exercises is a tiny correction which has not relevance to detect. All right. So, if you want to keep pushing this effective field theory interpretation, then this is valid below some cutoff. So, if you want to go beyond cutoff, you must modify, that means you must increase, add some extra degrees of freedom, extra matter fields, interactions and so on. Suppose you could keep doing this, then one will say, and infinitely, I mean no matter whatever scale you are, if you get inadequacy, okay fine, I can add something more and keep doing it. Then you will say if such a theory can be done, then such an effective theory can be said to be UV complete, ultraviolet complete. This property is distinct from renormalizability, because for example, you have quantum electrodynamics by itself, which is renormalizable, but it is not UV complete. It has the so called Landau pole. Of course, this breakdown happens at some ridiculous order of whatever 10 power 200 GeV or EV whatever. So, it is not physically relevant, but as a mathematical property of the theory, QED is not UV complete, but QCD is. Non-abelian theories are, because the coupling constant decreases as you increase the scale. So, they are okay. So, perturbatively non-renormalizable gravity is perturbatively UV incomplete, because I cannot keep adjusting the scale. Okay. But now there is a problem. The Planck scale is the highest scale that we know, which is where gravity gives this natural scale, which was already given by Planck himself. The Planck mass is of the order of 10 power 19 GeV. For comparison, our currently accessed scales in LHC, for example, is about 10 power 4 GeV, 10 TeV roughly, and speculated scale of grand unification is 10 power 15 GeV. So, this is even above that. So, up to that, at least we have some idea about what the matter content is, what the interactions are and so on. Coupling constants will run and so on and so forth. But up to that point, we have some idea. Beyond that, we don't know what happens. So, once we reach the scale of cutoff scale of Planck's mass, we have no clue what the effective quantum gravity could be. How do we modify it in order to make it to go beyond? We simply don't know. So, one alternative is to say, okay, either you have some different theory, embed this theory into something else, as will happen with string theory, or gravity better be say that gravity should be UV complete. So, whatever quantum theory of gravity or calculational scheme we will choose should be such that it is UV complete. So, that will be a desired property in order to avoid this issue that gravity deals with scale which is higher scale beyond which we do not know anything right now. And so, if you push the way of calculation this way, then you have to expect that such a theory, quantum gravity theory should be UV complete. So, that is one of the things that we feel. All right. So, we have sort of gotten the motivation part, we have gotten what happens in the first simplest assumption you made about calculate Feynman diagrams and so on. You get into problem, but you can manage the problem, but you cannot manage the problem because unless something else is true, namely UV completeness property is there. All right. So, what are the special features of gravity? So, this was perturbative approach which told us that this is how far you can go and this is what you can expect. Now, Einstein's equations will of course cover all kinds of solutions. There are huge variety of solutions of various types, the benign solutions like Minkowski space or small perturbations about it, or even solar system gravitational fields and so on. But also it has highly curved and very strongly dynamical spacetimes. Those are also solutions of this. For example, in the early universe you will see that the time evolution is extremely rapid. You also have very strong curvatures when the object gets very compact. So, these geometries also come. Now, once these are there, you have the situation that these are too violent to be used as background to do perturbation theory about. Because perturbative approach will say you choose some background, say g bar mu nu, and to add an extra term and you can compute those corrections from that. Now, those corrections can be computed because now our differential equations, Green functions are all going to be decided by the background geometry. The background geometry is too violent, I mean either too sharp curvatures or too strong time dependence, then you cannot push this idea further. You cannot do the perturbative calculations there. Now, this is a feature which is gravity presents that such situations do exist, and therefore, you need to have a formulation which will be at least have in principle possibility of going beyond perturbation theory. So, this opens the possibility that we should have non-perturbative quantization, but moment you say non-perturbative quantization, it also opens the possibility that you may have UV completeness in a non-perturbative fashion. This is the idea of infrared safety, namely you imagine that there could be non-trivial fixed point, and therefore, you could have a theory which is UV complete, but it is not sensed through the perturbative calculations. Second feature is that the perturbative background or any background you choose and make small corrections, which is all that we know mostly in actual practical cases, is something that you can do it, but it will only give you answers which are in the equivalence class of the background field. For example, if you do background Yang-Mills field and do perturbations around that, then the answers that you get will be background gauge invariant or covariant. So, that will only connect the background that you chose together with its gauge equivalent class. Now, gravity, if you keep doing that, you will take one background, you will find it, but there are many more inequivalent orbits and there is simply no way you can access from one to the other, because any calculation will at best fit you within that particular equivalence class. So, therefore, these things are left outside, or you have to keep finding out each separate case and do the calculation. Ideally, you should then have a situation wherein you do not have to presume any particular background. Now, one comment about background is also that moment you choose a background, it becomes imperative that you choose only those diffeomorphisms which preserve the background, as simple as that. That is why you say Minkowski space-time background is there, you will always choose something so that the global symmetry is Poincare symmetry, you preserve the background. Whereas gravity says that no, general covariance came in the first place because you want to avoid arbitrary coordinate transformation, that is because you want to get arbitrary accelerations which can be equivalent to other observers. So, general covariance in the sense of arbitrary coordinate transformations or diffeomorphisms is essential part of general relativity, and therefore, it cannot exclude any particular class. Now, if you want gravity to be fully interactive, that is back reactions are not eliminated, background field calculation typically will not affect the back, will not incorporate the back reactions on the background. So, if you want to not have that, then you better have something, your framework should be something which is background independent. That is what something one would like to have as a property of addressing quantum theory of gravity. Remember, none of these features are there when you talk about all other three interactions that you have, because they always have a fixed background which is given. Diffeomorphism called background space-time is inert, it doesn't do anything, it just sits there and allows you to make measurements. Whereas once the gravity is there, space-time is dynamical, it's changeable, and you don't have that luxury. There is other issue which comes about, which is again a qualitatively different issue, so-called problem of time, which again as a statement it sounds sort of philosophical. I will just mention, and I will not get into sort of trying to precisely define what the problem is and so on, but I will indicate where the issue arises. Now notice that role of time for non-relativistic case of course was that time is absolute in non-relativistic physics, which means whatever time is there you choose the time coordinate and all observers can use it without any, I mean at best they will differ by constant shift, but the rates are same and time is there. So we have no confusion about if I say something happens at such and such time and you say something, there is no confusion about it. We can use the common time. Special relativity made the tagging comparison dependent on the relative velocity, and that's the effect of time dilation that we all teach the students and tell them the examples of muon coming down and how the time dilation works and so on and so forth. But that is lesson is that the time stamping of events that one observer does are not necessarily immediately translated literally. You have to allow for the time dilation labeling. Gravity makes it worse, because at least these are of the two observers who are in the relative motion can have this effect. If you allow arbitrary motion, which is what the gravity will allow, then these timing effects also depend on the local gravitational field, again as seen experimentally by Pound-Repka experiment. So the clock rates change, that is when you compare two different clocks you get a mismatch between them, which means the time notion that we assume so much that all the timing notions which are there are commonly available for typical earth based experiments, except now we talk about GPS and so on, you have to worry about all these effects which are there. So JR makes it independent of local, I mean dependent on local gravitational field as well, and remember local gravitational field is not fixed, it is variable in principle. Okay. Come to quantum theory. In non-relativistic quantum mechanics, Schrodinger equation is a postulate. You say that there is a common external time stamping and the states will evolve or operators will evolve as a function of this time in particular unitary fashion, etc. Now, special relativity, you try to naively extend this, just take the equation, make p square, I mean use the dispersion relation, get the Klein-Gordon equation, but this naive extension leads to negative probabilities. So again you need to do something different than what you did earlier. This is overcome by recognizing that actually this is signal of existence of new entities called antiparticles, and if you are able to do some, you can build a Hilbert space in as a particle excitation, then you can take care of this problem, and we simply have to realize that the relativity, special relativity implies that there are particles as well as antiparticles, and I should think in terms of the Hilbert space of the quantum theory as a Fock space. So you give me some vacuum, I have Kirchhoff operators and build a Fock space based on that. This of course, building this Fock space requires time to be chosen. So typically it will correspond to say whether you have to choose what is the time field with respect to which you define the frequencies, and those frequencies will be h cross omega of that will be energies, and you want to talk in terms of that. So omega itself depends upon what is the time chosen, which depends upon which observer is doing that. As long as two observers are in the relative motion, you are still okay, because the Hilbert space construction that you do for your subsequent calculations are unitarily related. So it is not a big deal, you can manage. However, once you have accelerated observers, that is no longer the case. Now you got inequivalent Hilbert spaces, so you don't really know exactly, I mean your conclusions will be different. One will say, okay, there is a vacuum state, other will say, oh, you have thermal state. That's the Unruh effect. So therefore, the notion of time which is coming as innocuous thing about labeling thing, etc., enters also quantum theory at a very postulational level, and then it has the consequences of the type which are, because the entire construction of quantum theory depends on that. Okay, so this is roughly the problem of time in the sense there is no global time which is given to you, it is observer dependent, and every observer will have to be given, and it is not only the time, but all the entire causality notions are dependent on observer, because the metric depends locally on, varies from point to point. So in dynamical geometry, the clocks, rods, causality have no a priori existence, there is no given existence from which you have to factor that in while building the theory. So you can't say that this is kinematical structure given to me, based on that I do my calculations and make my predictions. No, this has to be factored inside already, except for situations where you can neglect it, which is where all the standard experiments are done, and that situation is benign enough, that is fine. Now, what are the different efforts which are gone into building a quantum theory of gravity? So, there are two main approaches which are there. One approach is the so called canonical quantization, and the other approach is the path integrals. These are the two most common approaches which are used as a process of quantization, that is as an algorithm to start with the classical theory and construct a corresponding quantum theory, which means construct Hilbert space, construct bunch of observables, and then you can calculate your expectation values and fluctuations and so on and so forth. So, you have to construct which one is the appropriate Hilbert space and observables for a given classical system. Of course, one reason to, when you say that I am quantizing classical system A, it means that your theory must have some ways to identify states which will correspond to the classical theory that you got. So, that's what it means. Otherwise, you will just construct some arbitrary Hilbert space, arbitrary operators, and I will do all the representation theory of various algebras, but that has nothing to do particular to do in any particular system that I want to talk about. So, that link has to be maintained. Now, if I start writing this canonical quantization, etc., it will just take me too much time. So, I will not. The idea is the following. You think of the space-time geometry as though it is some data that there is a space. So, at time slice you choose whatever time. So, time is an arbitrary coordinate here, but choose some coordinate. In that coordinate, there is t equal to constant defines a surface. That is a well defined step. It will vary from place to place, that does not matter, but in a local place I have defined it. Having done that, I have got a notion of what is space and what is time locally, meaning what is time like coordinate, what is space like coordinate. The physical measurements are always the line element delta s square is equal to gt t dt square plus spatial part. It is never the coordinate intervals which are physical, only the invariant intervals are physical. Now, if you can do so by parameterizing the metric, what is known as in terms of ADM decomposition. So, you can write the G00 part of the metric as some n square, then the G0I part, time and space part, can be written as some vector, and the space part can be written as another metric. That metric has to be positive definite. Remember, in the general relativity or space time metric, the signature of the metric is always Lorentzian. So, there is always one time like direction and three space like directions. So, when you decompose this way, you are saying that the space block is necessarily positive definite, which is what makes it space like. Otherwise, any matrix I can write arbitrary, draw the block from, and that does not mean anything by itself. Now, if such a thing is there, you can decompose the Einstein action itself using this parameterized form of components of the metric and write in the form. So, it looks like you can define from it velocities, you can define from conjugate momenta and put it in the form of a Hamiltonian structure. The difference is that because there are going to be, you will find that there are 4 arbitrary parameters which come which do not have any velocities. So, like in electromagnetism, when you write, you do not find in the action any velocity corresponding to A0. So, that is an indication that the theory that you are writing, covariant form of the theory that you are writing, is actually a gauge theory. It has the apparent variable, the variables that you list are not necessarily the physical variables, but there are some redundancies in the description, and those are the redundancies which are we call as gauge theories. And there is a systematic way of finding out, starting from an action, how to find out whether the theory has constraints. It does not have this notion of having velocities not being present indicates what is known as constraints, and this constraint theory is what is analyzed by Dirac. Usually we no longer teach this in our classical mechanics course. Whenever I have taught, I have always given 3 lectures on that topic, because I feel that all fundamental interactions that we use are all gauge theories, and people should at least know roughly what is it about, apart from saying that mu goes to mu plus del mu lambda or corresponding non-abelian transformation. One should know a little bit more about what the structure means, because that is a structure which is essential to say which quantities are physical observables. Like mu, even if you write as an equation, is not a physical observable, if mu nu is, and likewise traces of f square etc. for non-abelian cases, or you can write the holonomials. So, in order to isolate, identify what are the physical variables and physical observables, you need to go through this step, and that step is most clear when you write in terms of Hamiltonian formulation or the so called canonical formulation. Now, the fact that you had arbitrary general coordinate transformations permitted gets reflected into a technical quantity called this constraint must satisfy certain algebra, and the algebra closes in some particular fashion. I am sorry, I am not going to write this equation, I can write it, but that is not going to illuminate much. So, it is sufficient to say that you get a Hamiltonian formulation, but with constraints, and with these constraints satisfy certain algebra, that is a mathematical property which exists. And now, you have to take such a theory and quantize it. So, this is the canonical couple say, first put the theory in the canonical form. This is what you do for ordinary particle mechanics. You always say that write the corresponding Hamiltonian, identify Q and P, then postulate that Poisson bracket QP goes to minus I over h bar times commutator, and that is the Dirac procedure of quantization, something that we teach the students and do it all the time. Here you have to do the same thing, except you have to worry about the fact that what you are quantizing are redundant variables. So, their quantization is fictitious. They are not the ones which are going to, their values are not going to give you the physical entities that you want to confront with experiments. So, now this notion of quantizing, simplifying the problem and going to variables at classical level itself, which are already physical variables, there are no redundancies, you have fixed all of that. So, it is like saying that in electromagnetism I go to the transverse vector potentials alone, I have fixed the gauge, everything is given in terms of only that. So, I have classically fixed the gauge and gotten to the fields which are physical degrees of freedom, and then only quantize those. Other is to say, no, I will take all the AMUs whatever they are, but use the fact that the Gauss law, namely divergence of E equal to 0, is imposed as an operator condition on the set of states that I choose. So, that is known as Dirac quantization. You impose the constraint as operator conditions on the Hilbert space that you first construct as an auxiliary construct, and say the solutions of these are the ones that I am going to take as my physical states. These two processes do not necessarily commute, and this becomes a challenging issue for gravity, because gauge theory aspect of gravity is even more complicated compared to non-abelian gauge theories. So, after getting these physical sets, etc., the space-time interpretation, now we come to the mathematics has gotten up to some level, you have to interpret back to physics, you have to construct my space-time in which I do experiments. That step is again highly non-trivial, and only in some simplest cases such as homogeneous cosmologies or essentially what is called mini superspaces. So, you reduce the infinitely many degrees of freedom to few degrees of freedom, and there you can push this formalism and say, do you get sensible results or not. So, that is as far as one has gotten. Okay. So, that such a method can be applied is demonstrated in the, yeah. The reason is that, see, you put, you impose, let us say, particular constraint acting on states to be equal to 0. Okay. So, you construct, I mean, how should I say, electromagnetism, you will say simply I have some all possible square integrable wave functionals of mu, and on this I am going to impose del dot E acting on that equal to 0 to select the subset. Now, in the corresponding thing that you do for gravity, you will get the solutions of these equations which are not in the Hilbert space, they are not normalizable. That happens because this operator form of this constraint is, well, Sachin is not here, yesterday we talked about all these issues about self-adjoint operators, etc., etc. So, this spectrum happens to be continuous, therefore, those guys, there are no states which exist there, which means they have to be understood in a different fashion as distributions. Now, you can do that, you can therefore construct a space of solutions, but then that has no built-in inner product, so you do not know how to interpret that as probabilities. So, you need to introduce one more new inner product such that you can construct your quantum theory. Now, how do you choose that inner product? There are many possibilities. So, you say that I will choose some set of observables which I want them to be physically there, and my inner product should be such that these observables are self-adjoint. So, you can see you are faced with huge possibilities. The only way you can restrict it to say that these are the observables I want to be available to me to make measurements and interpret, then my inner product should be chosen like that. Now, can you always do that? When can you do it? When can you not do it? It's where the technicalities come. It's only after getting that mathematics right, you can talk about what the observables are. What is the, you can confront with the experiment. Say this is the prediction of the theory. Now we'll go and check with the experiment. Experiment don't care about your calculations. Experiments are whatever they are. Here we don't even know exactly what experiments to do. I will come to that, make few comments on this in the end. as I said in the beginning, we don't have any clues from experiment, and that's why there is no direct reason as to why you should quantize gravity. That was the purpose of initial part. So we have no clues as to what we should expect. So we have to find something else very indirectly and see. So the two places which I identified as conceptual issues where classical theory is not adequate, you need to quantum theory. So ask the question, can I get my new framework with all these things done, something which will A, resolve the singularity, and B, when the correspond to saying that late time or whatever time I use or large volume of the universe, the world looks like the world we know. So these two features, if I can get it, then I am done. Then at least I have a candidate theory that my mechanisms have worked. Now this thing is non-trivial, and I will comment on that when it is done or not. Yeah.
G0I and Gij.
Yeah.
So after you're done with this process, in the classical limit or something, you will reduce to that metric, or is that not the
this is not a fixed metric. That's only a parameterization of metric. The Gij is a free variable, like generalized coordinates.
Okay.
So my configuration space is space of all possible Euclidean signature metrics, and their time derivatives with the time that I have chosen in my calculation are my conjugate, the velocities and the conjugate moment I define from that. So it is not one particular solution I am looking at. Just as in standard phase space calculation, you don't look at one trajectory. You look at, give me initial condition, it will tell me how the trajectory evolves. So all possible initial conditions are allowed. Therefore, in this sense, the Hamiltonian formulation or canonical formulation is background independent. You don't presuppose any background, for background space time, I mean.
So if I want to then apply it to a situation where there is a, like a stellar object or something, then I choose the initial condition so that I'm in that physical setup.
Not initial condition, because that is still a classical picture. What you need to do, now you have gone to the quantum theory.
Right.
Once you go to quantum theory, you have to identify what are the states which will mimic the classical picture. See, when you say that my classical electromagnetic field is so many volts, etc., you measure, what is the corresponding quantum state? How do you describe that? So you say that there are coherent states, and there are coherent states defined in a particular fashion with certain properties with wave packets and so on. So you have to identify what are the states within your quantum theory, using which if you probe the observables, namely take expectation analysis and they will match with the experiment. So the interpretation is in terms of that. So here you want to construct space-time in this average sense from the observables you build in the quantum theory and say that this is how my space-time is going to be, the geometry is going to be modified because of quantum effects. And if I can find out, distinguish what is the changes and how much error, then there is a hope that one can.
And we know how to make that mapping?
No, that is one of the, they come to the part. That is where the things are challenging. How to identify this is not very clear. Except for our simplest cases, the FRW case, for example, this has been done. So I will comment on that in a minute here. Yeah. So in loop quantum cosmology, gravity, the setup is of this type, Hamiltonian formulation. I will not go into even writing the first set of equations. It changes the variables from the usual 3 metric and the corresponding time derivatives to something called, make it look like, go from, instead of metric formulation, go to the Fjellwein formulation. So use the frames as the square root of the metric as your basic variables. And using that, you can find out that therefore introduces additional local Lorentz transformation as the gauge symmetry. So you choose different variables called SU2 connection and its conjugate variable, and go through the lot of calculations and so on. I have talked about it here before, but today I am not even going to try it. So there are different set of variables. So your procedure is going to be different kinds of variables you will choose. Okay, it's going to be canonical. Given that, you can write down the structure in terms of getting constraints and all is exactly same. So that feature does not change. What changes is the actual details of what the structure of the constraints is. How you simplify that part changes, and therefore the construction of the quantum theory changes in the technical level. Okay. Now, so the loop quantum gravity, which is based on this new set of variables and new method of constructing the quantization, has been used to have two of these issues addressed, namely how do you get the black hole entropy? Does it correspond to saying that the microscopic computation of this corresponds to, in the large black hole limit, corresponds to Bekenstein-Hawking entropy plus corrections. So this is one problem where it has been achieved. Also string theory is achieved. I will come to string theory in a minute. And also it has been used for this all step-by-step calculations that I indicated, constraints, their imposition, inner product, observables, all of those steps can be explicitly carried out when you are talking about the homogeneous isotropic space-time with one matter degree of freedom. So, it is the smallest possible thing you can do, and there are little bit more than many superspace models are there, but this is where it is most clean and with completely done. And there the indication is that classical theory indicates that you should have initial singularity, whereas quantum theory says no, singularity will be resolved, because as the thing gets smaller, universe gets smaller and smaller, the energy density increases, and once it reaches critical density, it bounces. So, you no longer can use the same classical geometrical picture that you had, it is superseded by different variables whose expectation values are going to look like classical theory, close enough to the bounds. After that, it is no longer that picture. So, it is basically saying that moral of the story is your space-time geometry itself under this extreme condition will no longer be a viable model. It has to be replaced by something else, and that something else has to be worked out in case by case basis. There is no general prescription available. So, that is the modification that comes. And black hole entropy notion again is a question that the thermodynamics said that there should be some, I am looking at this because I also have to take the shuttle. So, the thermodynamics says that there should be statistical mechanics under it. So, the question is what are the degrees of freedom which are there. Classically there should not be anything because nothing happens there, I mean that nothing comes out of that. So, there should be quantum degrees of freedom. Now, are those quantum degrees of freedom strictly sitting on the horizon? It is just little bit outside, little bit inside, it fluctuates. In what way does it fluctuate? You need to characterize it. Now, all the calculations which typically one does in terms of Hawking calculations also are done in the context of background geometry, which is say Schwarzschild geometry for example. It is done in semi-classical, so you are not considering evolution. Essentially over the time scale you calculate it is stationary, so you can do all the standard field theory calculations and get the answer. So, black hole understood there is understood as having event horizon, which is a global notion which talks about I need to know the entire space time, and then I will know what region of the space time is called a black hole, which region is not. Its boundary is the event horizon, and all these thermodynamic effects etc. are supposed to be taking place in the vicinity of that. So, first step in this LQJ calculation is to replace that notion by saying that I do not need to wait for the entire space time to be built. I will look at quasi-locally, and it is enough to consider a model which will capture only that. And that step has been done. It is in the notion of so-called isolated horizons. It is a slightly different model of black holes. It does not need to find out what is the event horizon. So, black holes are not defined by event horizon in these calculations. They are defined by properties that event horizon defined black holes will have in the quasi-local region, in the vicinity of the what would be the horizon.
Sure. Can I ask a question?
Yeah.
Oh, so, shouldn't we expect the quantum theory of a gravity to explain why the black hole entropy should be like an area, like?
Yeah.
Or is it just matching the microstate count and getting the area sufficient? Like why?
Well, that is what it will mean. The first step that will have any quantum theory will have should have within itself. So, first step is identify what do you mean the black hole state within your quantum theory,
right.
And then show that by doing whenever the black hole is in equilibrium. So, thermodynamics is potentially viable.
Yes.
Get an ensemble, microcanonical ensemble typically, count the entropy and show whether this entropy goes as you would expect from the classical theory. That is the first test, so to say. If you do not even get that, then your quantum theory is not capable of addressing that issue. What it will additionally give is that A, further corrections, and B, what is the nature of the microscopic
But
states?
from this computation you say that it's exactly the Bekenstein-Hawking that we get.
No
correction.
Get plus corrections, of course you get.
Oh, okay.
Yeah, sure. You get correction. Leading term has to be that.
I see.
Yeah.
Okay.
I mean, there are few technicalities, but I think I will describe it. I mean, there is a ambiguity parameter, Barberi Mirzi, and you have to adjust and so on and so forth. So, let me not get into that. The point I am trying to make is that there is a quantum theory based on canonical approach, quantization, which is capable of finding out or addressing the issue, explaining black hole entropy from microscopic accounting. Such a thing exists. So, to that extent, quantum gravity has progressed. This is not the end of story. There are many things to be done which we do not know. And secondly, the case where singularity resolution part is there, again the simplest possible case, you can push this argument completely and do it. So, that is what has been achieved in this approach. So let's look at in more general case, we simply don't know how to proceed. I mean, the formalism exists and you are trying to build various things and so on and so forth. Semi-classical sector to identify is, is the most challenging part which is there. So that we don't really know in this approach. Second approach of quantization is path integral quantization. So intuitively it is most transparent. The full transition amplitude between two states that you choose is given as some more possible paths weighted by a phase divided by action divided by h bar that everybody knows and we are sort of most familiar with, and that's the easiest way to sort of morally quantize the thing without worrying too much about many technicalities. Because the action is larger compared to h bar, when that happens you say that, and I mean the variation in action is essentially close to 0, then these multiple paths will interfere and only the parts which are close to the classical paths, so that delta s is close to 0, a stationary phase approximation, is what will be picked out as the net answer, which means your transition amplitude is dominated by classical paths. So you are basically saying that I am very close to classical theory. So approach to classical approximation is most transparent and most natural in the path integral approach. And the quantum corrections can be, leading quantum corrections can be obtained by going one order higher, calculate the determinant, and from that you get the answers. However, the technical challenge here is path integral. For the usual cases it's fine, it all works, you can derive from this effective action, Feynman rules, diagrams, and once that is done you forget about how you derived it, simply calculate the diagrams, or now even better go to the programs and do it. The problem is that when you come to gravity, the path integral itself is ill-defined, and that has to do with the fact that even if you do the Euclidean continuation, which is what normally will make action going to minus the action when your t goes to minus I times t Euclidean, that action is bounded below for all the other theories that we know. That is not the case with gravity. So even after making this Euclidean so that you can talk about it, so this action is still continues to be unbounded below, which means the action per se doesn't exist. I mean the path integral doesn't exist. Okay. Again, there are different ways of doing it. Yeah. Yeah, sure. I agree. I agree. I agree.
Then this unbounded problem will not arise because you are discretized it.
No, unboundedness problem is coming because you have the conformal mode of the metric.
And will it also stay in the discrete
yeah, because that's the extra degree of freedom, which is, so you're discretizing the space-time part, right? Lattice is, but the variables which are taking values, I don't know how the action looks like in the lattice case. I just don't know. Maybe if it is not there, the problem will come somewhere else when you take the continuum limit, and the basic problem doesn't go.
But we don't need to take the continuum limit even in case of gravity. If you take it as a
I don't know how it works in gravity. I honestly don't know. So I cannot. I would just suspect if the problem is physical problem, it must manifest in some form or other. There are ways people handle this in practice. Is one is to say that I look at only the small fluctuations about the background. That's one way. So you truncate the other things. Background is frozen. And otherwise you say, okay, there is a possibility. Who tells me that my naive dg that I write, the measure that I write is the correct measure? There is nothing which says that it should be that. So try to modify it. Now I don't know if lattice theory effectively modifies that also and then handles it. It's possible, that possibility exists. So that is something that needs to be done. Again, you can do it case by case in some cases, but how much generally it has been done is where the issue is. I agree, it's possible, and that's one of the methods people do try to address it.
Hello.
Yeah.
Two questions. One, from the LQG calculation, the corrections that one gets to the Bekenstein-Hawking entropy,
Yeah.
are they of the same form that the string theory gives?
No, they're different.
Completely different.
I mean, they have a similar structure, coefficients are different.
But you said there is an ambiguity parameter.
Oh, that ambiguity parameter is fixed at the leading order itself. Once that is fixed, the next correction, for example, is independent of that ambiguity parameter.
Okay, so the subleading terms
Yeah.
disagree with each other.
Yeah.
Okay, second question.
Yeah.
Second question in the
That is
Euclid-
Ashoksen's calculation. Yeah.
Sorry?
That is Ashoksen's calculation.
Yes.
Yeah.
In the this Euclidean path integral, you can always take a compact space, right? That is that way you can.
No, compactness of the space is not a problem. It's the when you integrate over the matrix, this is the conformal mode. You can write the metric as e to the omega square times some fixed metric. You are integrating the fixed matrix as well as the omegas, right? The conformal factor.
And you're saying that,
That factor is the one which, because this Weyl transformation of the curvature itself will do that in dimensions greater than 2.
okay,
So
and,
dimension dependent statement.
and that conformal factor is leads to this
Action being
unboundedness.
unbounded below, yes.
Okay, thank you.
So answer to the first question in the sense that yes, the answer to the corrections calculated in string theory and loop quantum gravity are different. My take on that is that the model of black hole, what you mean by black hole in these computations is different. Whether you are computing the same degrees of freedom or not is also not very clear. So I would put it at that level. It is a priori not necessary that two answers must match at the correction level. Leading term must match because that's semi-classical. But correction level, it depends how you are exactly, whether the two models of what is the underlying structure of black hole is same or not. That is not clear. Even after you look at the microcanonical versus canonical, that correction is.
There's an ambiguity in the definition of what you mean by area when you have corrections.
That is again, I mean, yes, and people like to use the area contains the G Newton or LP part, and that G could be running and so on and so forth. Ramesh Kaul always talks about that. I have never fully accepted that. The reason being, I do not know whether the running will come if you say that I am defining my coupling constant with some process at some momenta, such and such value is there. But that's not how we define Newton's constant. I don't know what process you will take to say that these 3 graviton vertex or 4 graviton vertex at such and such momenta will give the value to Bg. If that is not the case, it's not clear to me what is meant by renormalizing G, running of G. So it will depend upon the way you calculate the thing. If in certain calculation schemes, yes, that will happen, and some other calculations it may not happen. So it's not something it's not God given that everybody must run. It depends how you define the parameters. So this is something which I have not. I mean, we have discussed many times. Ramesh Kaul always likes to say that. He also says that well, LQG has this parameter gamma, and the image parameter, and that is linked with the Neayan topological term. So string theory should also find it somewhere, but there is no such parameter. Whether it is true or not, I don't know. So I mean, these are more. I would put them as more dependent on calculational scheme as opposed to what I would say a physical effect which should be there or not. So these are models of underlying microscopic structure. Depending upon what you choose, you will get different answer. There is not necessary they must be same. One can still continue and see how much do they differ, when they differ, what, how you understand different aspect. That part is a separate issue. Okay. However, path integrals also offer tremendous. I think I'm going to miss the bus, but okay. Thank you. So the path integrals, however, offer tremendous flexibility, formal flexibility. I mean, that is something which makes it path integrals very attractive, especially people who somehow feel that there should be topology change for whatever reason. So consider a path integral. So to indicate what these things are, so let's consider a path integral. But now we are talking about path integral for gravity in 4 dimensions, okay, not 2 dimensions. Metric fields are defined over a 4 manifold. Manifold is separate from metric. Remember that this structure has to be different. Manifold is manifold, space-time is different. Metric sits on top of manifold. Manifold is first given and metric is put on top of that. So you define some 4 manifold. It is bounded by 2, 3 manifolds. Like you take a sphere, it will have, I mean, a cylinder, a disk, you have 2 different boundaries could be there. So you are taking 2 fixed manifolds which are boundaries of this, okay? No, not necessarily. Could be arbitrary 4 manifold.
But does it have something like a Minkowski signature?
No metric. That's why one should be very clear that metric is bound after you choose the manifold. Manifold just allows you to do differential calculus. You may or may not put metric on that, you may or may not put symplectic structure on that, you may not put any distinguished tensor field on that. That you put is something extra that you do in order to do something else. So manifold is just manifold, it doesn't come with any baggage of space-time. On top of it, you can put, now say that I want to define, make it into a space-time or space, depending upon what kind of signature I want to put. So that is something which I choose. And the idea of path integral to say that give me this manifold, I consider all possible metric tensors that I will put on that, and I want to sum over them in some fashion. By some action, etc. I will write, or lattice form or whatever. I am coming to that, hold on. So this is just the initial scheme. There are 4 manifold with 2 boundaries. That is that. And now you can say that I can now the possibilities that even before putting metric, I can have these three boundary manifolds, they could have different topologies. One may be a sphere, one may be plane, one may be a sphere with two holes or whatever, or two different things. The remaining four manifold which is interpolating between these should first of all admit this as boundaries. Secondly, I mean the typical example one talks about is the pants diagram, so to say. You take these two pants, attach them at the, okay, here is the one pant leg, second pant leg, second one, and this is joined together. Okay, or so you can do that. So and you can have any number of such holes. So you may have one boundary which is made up of several holes, one boundary may have only two holes, and there is some three manifold which two manifold which interpolates these one dimensional manifolds. It's a lower dimensional example I just described. Is that clear? A boundary of a manifold of n dimensions will have n minus 1 dimensional manifold. So if I am talking about 4 manifold, its boundaries can only be 3 manifolds. The 3 manifolds could be whatever you want. It could be disconnected, connected, etc., etc. All these are possibilities. So we allow a priori allow those possibilities. So if the two topologies of the final manifold boundary 2 and boundary 1 are different, one will say there is a possibility of topology change. Okay, because now it is saying that I am now to find out transition amplitudes for the matrix which you defined on the boundary 2, boundary 1, and the transition probability is given by the path integral done over integration of all possible matrix on the 4 manifold with these two final and initial matrix fixed. Just as you have path in the ordinary configuration space, Q1 at T1, Q2 at T2, and arbitrary path. So arbitrary path is the analog of defining matrix over the 4 manifold. The two endpoints are the two boundary components, and the Q1, Q2 are the boundary values of the matrix that you choose. So you are now going to integrate path integration only those matrix which will agree with this boundary matrix, and otherwise will be defined everywhere, and a sum over all of this. They will correspond to labeling the states, possible states. When you talk about path integral k, I mean x1 t1 ket, I mean x1 t1 and ket, what does it mean? You are choosing two states. So here the idea is that the states are labeled by, or the kets in the Hilbert space or whatever you are going to construct, between which you are doing the transition amplitude, are labeled by the values of the metric that you will take on this boundary surface.
There could be a time t equal to minus infinity and plus infinity.
You can do that. There is no time here because you are not,
No,
the
but
time
you-
depends on, so just take two boundary components, boundary 1, boundary 2. You can choose that. So orient, I mean, that will require time orientability, that will require the metric to be Lorentzian signature and so on and so forth. But if you are going to say that I will define this by Euclidean continuation of some form, then it need not even exist in between. So the point I am trying to make is that it is conceivable that you can have transitions done with topology change. This is only a possibility. You can also say that the metric which sits in between need not be invertible, somewhere it will become degenerate. In which case now it can change signature. Otherwise signature I cannot change continuously. So metric can become degenerate. All right, I will allow that also. After all, one is supposed to integrate everything inside, so I can integrate over this also. This is only desire, it is not actual. Okay, one would like to do that. So this is corresponds saying that I can have admit integration of those space-time which are degenerate matrix. So exotic histories of this can be imagined. So that's the advantage of path integral approach to writing quantum singularity. And you will simply say that these are the possibilities which are conceivable. How much I can implement is a different story. However, even if you write such a thing, you might find that the path integral that you write has no extremal solutions, so-called saddle points. If that is not the case, it is not going to be dominated by any particular geometry, whatever interpolating geometry you choose. Okay, that may or may not be the case. You might have to sum over various things, then you will have to worry about what is the interpretation of such objects. You don't know. So advantage of path integral saying that h bar going to zero limit, I am going to get a classical solution is no longer guaranteed because such a thing may not exist. So if you allow arbitrary kind of geometry, it may not happen. All said and done, no non-trivial examples of these exotic 4 geometries, dimensional histories is available. People have done examples in 2 dimensions, 3 dimensions, I think only 2 dimensions. 4 dimensional case, there are also other theorems which will say that you cannot have a topology change unless in between metric behaves badly, but let us not go into those. So conditions under which this is, I was just indicating what possibilities can be conceived as a method of calculation, but are they realized? Answer as of now, no. So while path integral may look more appetizing that, oh, I can do topology change, signature change, do this, do that, after all integrate over every possible thing, well, you would like to do that, but you can't really do it. So that is the last statement. That's a fact as of now. Maybe later on it will change. Now, a very brief comment on string theory because yeah.
I can always restrict to, force the
Yes, you can also restrict the path integral to saying that I have the fixed topology initially, fixed topology finally, Lorentzian, I can do that. But yeah, I agree. That's a normal thing that one will do. I mean, non-exotic thing. But one appeal that people have about path integral, at least, and opposition to canonical method, is that canonical method doesn't allow topology change whereas path integral does. That's the kind of argument which comes, my retort is for that partly. That yes, in principle, but there are technicalities to be addressed. And it's not even necessarily an advantage that you should do that. There is nothing which says that by doing it you are going to get something better. It's just a desire which is there. String theory already we had a very long and very detailed discussion, so I am not going to, I will just make a couple of comments. So string theory primarily uses path integrals, but I should put a caveat here. These path integrals that they use are in 2 dimensions, the worldsheet path integrals. They are not space-time path integrals. So the conformal mode issue which arises doesn't arise in 2 dimensions. So that issue is not there. Secondly, the simplest first quantized string theory, which was already discussed, I am just quickly going through that. It fixes a particle spectrum which is classified by the isometric group of the target space in which the string is propagating, and that is typically taken to be flat space. So the target space isometric group is Poincare group. So you get the particle spectrum classified by that, and that happens to include in the critical dimension a graviton, spin helicity, I mean massless particle is spin 2 or helicity 2. So that was the advantage. Here is something you do quantize this string in this fashion. Here is gravity is included already, which is very encouraging. It also has the UV completeness property. It is certainly claimed, and everybody believes that. And the justification that at least I can provide is that the perturbative scattering amplitudes, that is genus expansion amplitudes you calculate, their high energy behavior is typically exponentially separation. Typically, I mean, again, I am not making it as a statement of theorem, because one can ask various questions whether target space is necessarily this, what happens if it is compactified, etc. etc. Large questions can be asked. But broadly, the belief is that this, for the simplest cases, it is true that the separation of the amplitudes is exponential. So it has a better high energy behavior. So therefore, you don't worry about this divergence problems which is present. And secondly, the dualities also seem to suggest that you may go from strongly coupled system to weakly, it will still retain the similar properties. Therefore, even non-perturbatively UV completeness can be there. Third argument for UV completeness is what I indicated initially, that as you increase the scale, and this occurred to me after Sandeep's talk yesterday, that string has this infinite tower of states. Let's take the simplest case with target space, which is Poincare symmetry. So that means no matter what scale I go to, there is always somebody available for me to correct it, which means the process of extending the EFT to larger and larger scale in principle can be taken to ad infinitum. Therefore, I can have UV completeness. So that's one qualitative argument to say why stringy part, because of the fact that its spectrum is of that kind, can be UV complete. Okay? So this is something which is nicer property of string. Black hole entropy already Sandeep discussed in great detail, and I just answered also that the question about the 2 corrections which are the leading corrections are, leading term is the same, but the corrections are not the same. That's because again the respective modeling of microscopic structure is different. Okay. In this direction, I checked with Sandeep yesterday. The singularity resolution part has not been done in string theory, in the 4-dimensional singularity, space-like singularities. Because cosmological singularity is something which is space-like, which means you start with a data which is well defined and smooth and everything, and when it tries to evolve, it gets into problems. So that is the thing you don't want. You don't want to start with nice thing and suddenly get into some problem. If you already have time-like singularity, you already have a problem somewhere and it continues, that's not a big deal. I mean, you already put in the problem by hand. String theory, however, is far richer in scope. It's theory of everything in the sense that it is unified theory. That's a positive for string theory, and it has huge amount of structure. I mean, it's hard even to sort of, I don't know, only practitioners will tell you various things which corner here, etc. does, etc. So this is, and quantum part of gravity is one corner of it. Of course, it is, since it is included in the particle spectrum, you see, it is considered quantum theory of gravity, but string theory has much more than quantization of gravity. There are other approaches, and almost for the end. Two other approaches which are more, one is causal dynamical triangulation. This is again a background independent approach. It uses Lorentzian matrix ritual. So idea there is to say that I will sprinkle points, so underlying structure of the space-time manifold is replaced by a set of points, but you impose some partial ordering which corresponds to causality. That feature you want to retain. And then you build, write again a path integral type approach, some more paths, choose the way you write the metric which is taken to be Lorentzian. I don't know details of this, and it's done all numerically. So as far as I could get, that what they achieved is that in 4 dimensions they can get the de Sitter space-time in the appropriate limit. This is what I have gathered, but I think Sachin would have commented a bit more on that. From osmosis would have known, but he is not here. So this is one approach which is also there, but all these other approaches are less both developed as well as less achievements in the sense of which problems they handle. So they are smaller in scope. Another one is this so-called infrared safety approach, which is non-perturbative functional RG. Bala knows more about these things. It seeks to establish UV completeness of GR by non-trivial fixed point without adding additional matter stuff in it. You may add, but even without that, you can still do it. So remember, UV completeness is the desirable property because the Planck scale is the highest scale of the known thing. You can either embed it in the bigger thing like string theory, or say I have non-trivial fixed point, non-trivial fixed point, non-perturbatively. Perturbation theory will not give you that anyway. So that is something which approach which is there, and Bala can correct and may comment afterwards that how much has been, to what extent it has been established. Okay, so in summary, so based on the context where quantum theory of gravity is strongly motivated, the one that I discussed initially, the minimal expectation from a quantum theory of gravity would be UV completeness, for the reason I just mentioned again. The complete black hole evaporation process. It's not enough to say black hole evaporates. Does it evaporate completely? And you start from the full simulation will be, you start from pure state collapsing, pass through the stage of formation of black hole, evaporation, and complete disappearance. Complete or may not complete. You have to go through all the stages. So far that has not been done. In 2 dimensions there are some results, but certainly not in 4 dimensions. So if that is there, then one will say that okay, you have got some resolution of one kind of challenge that the information problem poses. Other kind of information resolution that Surat talked yesterday, which was interesting, but I still don't understand it, I have to study it, which is altogether about how the gravitational theories process information, but that is something which it will take me time to digest, so I cannot comment, but it looks something interesting. But coming to black hole evaporation process, as a process, physical process, it doesn't violate information, is something that needs to be established not by taking only some this approximation and the approximation. One at some stage should have a full calculation of starting from collapse to end evaporation. And of course, resolution of cosmological singularities, which is one of the things which naturally arises. So with this, of course, we are not there yet, and thank you.
This resolution of cosmological singularities by bounds that you mentioned.
That's only the simplest case we have got it so far.
Okay.
Yeah.
In that, there is some parameter like time or something which you can continue through the bounds, or is done?
No, that evolution is done in terms of, okay, so there the degrees of freedom are the scale factor, which will correspond to volume. It's a homogeneous isotopic model. So there is only scale factor as a part of geometry and the scalar field which is there. So it's the evolution of the scale factor relative to the scalar field is what is being done. And scalar field is contributes to the density, energy density that you have. As the energy density reaches a maximum, there is a bounce present. And in the vicinity of that, you will get the uncertainties that you calculate from the Dirac observables will be larger than the uncertainty is larger. So you can no longer say that the evolution passes through the classical curve. I mean, if I were to one diagram is something like this. So I think it should go like this should be phi, and this should be scale factor or volume. And classically it will do that. This is the classical form you will get. You can write these equations explicitly, I can show you later. Here what happens is you will get in the quantum correction thing, you will go like that, and this will be the bounds. But this part here, the uncertainties that will, here they are very, very close, but here they will be larger. So this part will, so it will match with the classical picture for large volume, but as it comes closer, the geometrical picture that you had breaks down, because geometry has to be inferred from the expectation values of this quantity you calculate, and that will then picture like this. So that's what happens.
That 5 means the field value or something?
Yeah, it's a homogeneous field, because this homogeneous geometry, so 5 is just a number. And taken to be massless for the simplest case, so just 5 square root on this, P5 square root on this there. Yeah.
So why is phi going to 0 as volume goes to 0?
No, phi can change this. I mean, phi is like playing the role of a time.
I see.
Yeah, that was part of the problem of time. You are using what is called internal time to describe the evolution. There is no external time because constraint is there, so constraint vanishing means there is no external time. I didn't get time to talk about problem of time. One of them is this.
Any other questions?
Yeah.
Yeah, so sometime back I've seen an experimental observation regarding the gamma ray bursts. So the idea was that some of the quantum gravity theories predict that the space-time is quantized and there's some granular form.
Yeah.
So light from the long, like
Yes.
very far distance, they'll have some effect on that.
Yes. Yes.
And some of these observatory observed that and pointed out that they may not be, and some of these quantum theory, quantum gravity theories may be ruled out. So
Yeah.
can you comment on like such?
I can tell you what the
experimental-
mechanism is supposed to be. This particular result, but it's ruled out, etc. That part I don't know, but I can check it. The underlying idea is that, roughly speaking, the space-time is metric is fluctuating. If so, the propagation equation that you will either for Maxwell's equations or any other equation you write, even neutrino has been done. This was done again in I think early 2000 something. They will modify the dispersion relations. Once the dispersion relations are modified, the your propagation times and those things are going to change, or the signal that you will get from the light will change. A similar thing has been done also for neutrinos. But again, these are phenomenological models, in the sense you put in that I assume such and such effect, therefore I expect the dispersion theory to be modified with corrections which go as p phi square, etc., etc. I mean corrections to the dispersion relation. Instead of relativistic one, you will get additional corrections. So whether they go in the numerator or denominator, you will make some assumptions there, and only those things you can rule out. So one is not at a stage where you say, here is my quote unquote defined quantum theory from which I deduce it. We are not there yet. So in many cases, even black hole entropy for that matter, it is something that you have to put in extra input in order to identify what do you mean by a black hole in this vague quantum theory. You have to identify the state. You have to say that this is what I mean by black hole, and in context of this, these are the calculations I can do. So at some stage you make the assumption that A, classical properties of this surface that I choose are same as what you will get for classical black holes. So isolated horizon conditions will come there, etc. Then you will say that the state counting is done by saying that the boundary condition that you get classical is interpreted as a operator condition, and ask this question, what are the quantum states which satisfy this condition? Count those. That counting gives rise to the black hole entropy in the LQG context. So one doesn't have the thing that one unambiguous definition of what is meant by, for that matter, what is meant by Minkowski spacetime exactly, what is meant by Schwarzschild spacetime exactly. Somewhere you will have to say that my quote unquote moral coherent state is such that is peaked around these configurations. These are all hand waving, there is no derivation as such. So this particular thing, I don't know what they have ruled out exactly. I will take a look at that. But understanding is that the dispersion relations are modified, they are modified phenomenologically by putting extra terms, and some of those corrections which may be motivated and justified by saying, oh look, quantum gravity gives this or other theory will give that, etc. Those are ruled out. Very likely that is the case.
Okay.
Yeah.
Any other questions? Okay, so if not, let's thank Shyam for a very clear talk.
Thank you. I kept you waiting and many people have lost their bus. I think we have to go by the next bus. Sridhar has agreed to take it. So I have